So picking up where we left off yesterday, which was we needed to do this graph. I already have my graph done, so you guys are taking time to get your graph done. The bottom label is just the smartphones per household, because that's what we're talking about in this situation. In our chart up above, we had 0, 1, 2, 3, 4, 5, and 6 or more. So you'll notice across the bottom, my labels are 0, 1, 2, 3, 4, 5, and 6 plus is what I used. And then, 0 smartphones. Had 2% chance. So my bar is 2% high. We're making a bar graph, guys. That's all we're doing. At 1, it's 13%. So at 1, I went to a height of 13%. 2 smartphones is 24% high. So I went just below 25. 3 is 29%. So I went just below 30. 4 is 16%. So right above 15. 5 is 7%. And then 6 or more is 9%. Okay, just a bar graph, not a histogram, so my bars aren't touching, just a regular bar graph there. Okay. Now, we still have to go back and answer the question from yesterday, which is why I was giving you guys a moment to make sure you have your bar graph and everything. Because our question from yesterday not underline that very well, but would you recommend that the company concentrate on selling data plans for individuals or data plans for families? And specifically, it talked about families with 3 or more smartphones. So, with that in mind, thoughts here? Can you tell by looking at the graph? Can you tell by looking at the chart? Should we do a little bit more math? Where should they concentrate? Data plans for individuals or families with 3 or more smartphones? Okay. Here's going to be my question to you. What is the probability that a family has 3 or more smartphones here? 3 or more is going to include which numbers?
4, 5, 6, and 3.
Okay. 4, 5, 6, and 3, because it's 3 or more, yes?
Yep.
So if we look at the probability of 3 or more, so that means you're taking 29 plus 16 plus 7 plus 9. What do those values add up to be? $61? Okay. So probability of 3 or more, when you add up the 3, 4, 5, and 6 or more, is at 61%. What do you think? Should this company concentrate on data plans for individuals or data plans for families?
Families.
Families, yes?
Yeah.
Because 61% of the population has 3 or more smartphones in their household. So that leads us to, that's supporting the data plans for families, okay? That would also mean if we add up the 2, 13, and 24, we should be at 39%. Okay, so that has a lesser percentage there. So, answer is family plans. And I'm going to say family plans since, how do I want to say this? Households, since, okay, 61% of households have 3 or more smartphones. Okay. Okay. So that's a little bit of how we can look at experimental probability distribution. We're going to look at one on the next page, but how we can figure out the individual relative frequencies, or in other words, the probabilities, how we can look at it as a graph. So, top of the next page, just a little bit of practice here. And it says that suppose you select a student at random from the drama club and record the student's age. Define an experimental probability distribution on the sample space, 14, 15, 16, 17, 18, and then also we will graph it. So, with that in mind, okay, how do we find the probability distribution? Remember, probability distribution, you're assigning every item in the sample space an individual probability. So I need to know probability of 14, 15, 16, 17, and 18. How are we going to do that? Okay, we're going to have to add them up, aren't we? Because as it stands right now, I don't know enough information. How many total students are there? So we grab the calculators, folks. 37? Okay. So if there are 37, what is the relative frequency for the students that are age 14? How do we do that?
14.
Not 14 over 37. 4 over 37, right? Because there are 4 students in the age 14 group out of 37. And I just have percents here. Okay, and we're doing this. They tend to want us to go to percents. When we talk percents, I just have it written down to nearest whole percent. So what do we know about 4 out of 37?
It's like 10 point something, 11.
Okay. I have 11 also, so 10 point something that rounds up to be 11%. Okay, what about students that are 15?
19.
Okay, 19% is the nearest whole percent, and that's when you do 7 out of 37. What about students that are age 16? Okay, nearest whole percent is 27%, and that's after doing 10 out of 37 students. Age 17 students? 19% again, because again, you're doing 7 out of 37. And age 18 students? 24%. And that comes from doing 9 out of 37. Okay. Then ask us to graph this, yes? Graph it. This one's actually, I should have put this one first, I guess. This one's actually set up even better, isn't it? Because I was able to grab a graph that it's already marked at the bottom. We're graphing age groups 14, 15, 16, 17. That was our sample space. So what do we know about the bar for age 14? 11%. So you're making a bar that goes up to 11%. Age 15 is going to 19%. Age 16 is 27%. Age 17 is 19% again. And age 18 is 24%. Okay. Your graph finished up there. Again, this was experimental probability distribution. It's experimental because we are using data provided. That's what makes it experimental, because it's based on how many students in each age group that they actually surveyed. And then when you guys are ready, I'm ready to talk about binomial experiments.
Huzzah.
With binomial experiments, okay, there are 3 keys to a binomial experiment that I will try and take you through. Sometimes your question is just, is this a binomial experiment? Sometimes, there's more of a question of, to answer about our binomial experiment. Now, so 3 keys here. A binomial experiment is an experiment that consists of a fixed number of trials with the following features, okay? First of all, each trial has 2 possible outcomes, one of which is denoted as success. So kind of like yesterday when we were pulling the election buttons out of the box, right? You could pull out a TO button or a Henry button, if I recall.
Yep.
Okay. With that, we kept talking about TO, and so TO was a success. Anything else you grabbed was not a success. Okay, so each trial has 2 possible outcomes, only 2. The results of the trials are independent events. Okay, so what you do on the first event does not affect what you do on the second event. Okay, so for instance, grab you a TO button. You'd have to put that TO button back for it to be independent and not affect what you get the second time. And then the probability of success is the same for every trial. So, again, I keep going back to the first one we did yesterday. Probability of TO versus probability of not getting TO, it was 1/2 and 1/2, both times. So those probabilities are the same each time you run the experiment. Okay, so let's look at these. Our question here is just, is the situation, the experiment, a binomial experiment? And the first situation is this spinner is spun 3 times. Assume the spinner is equally likely to stop in any of the sections. Success is landing on a section marked go forward 2 spaces. And the copies did not turn out great on this particular one. They're definitely much easier to see up here on the screen, so use that to your advantage there. But let's go through and check each of the 3 options. Okay, so each trial has 2 possible outcomes, one of which is denoted as success. Do we have 2 possible outcomes here? That's the question we have to ask ourselves. Do we have 2 outcomes?
Yes.
So the outcome that is a success is go forward 2 spaces, right?
Go forward 3.
What is the non-success then?
Go forward backward 3. Or lose it.
Okay, so we have to make this into 2 groups. Success is go forward 2, right? Yeah, go forward 2. What is not success?
Anything else?
Anything else. Does that make sense? So 2 outcomes. So with the idea that success is go forward 2, not success is anything else.
Why?
Okay, so that means we have 2 outcomes. Everything can be grouped into go forward 2 or not that. Okay, so 2 outcomes. That matches up with the first piece up there. Okay. Second question. Are the events independent events? So in this case, my spinner is spun 3 times. Does the first spin affect what I get on the second spin?
No.
Do the first and second spins affect what I get on the third spin?
No.
No. So this means it is
Yes.
independent. Okay? One spin does not affect the next. Okay, and what's our third? Third thing we have to check? Got 1 and 2. The probability of success is the same for every trial. So what is our probability of success here? What is success?
1/8.
Okay. What is a success here?
40 on 2 forward 2.
Okay, so probability of, in this case, the success is go forward 2. Here's the deal. Is that always the same? Or can it change?
Oh, it's the same.
Every time you spin the spinner, it's going to be the same, yes?
Yeah.
Because how many go forward 2 options do we have? I think there's 2, aren't there?
There's 2. Oh, it's 2 8, sorry.
Yeah. There's 2, so 2 8s, 1 4th. But the key is it's not going to change the next time I spin the spinner. Okay, so it is 1 4th
25%.
each time. So, were we able to just check off each of those 3 points?
Yep. Yeah.
Yes. So, is this a binomial experiment?
Yes.
Yes. Okay, we can say that this is a binomial experiment because it met all the characteristics.
Will it always be like the success?
What do you mean?
Like-
They'll always have to tell you what we're talking in reference to, like what a success is.
Yeah.
Yeah, they'll always have to talk to you about either what a success is or just what you're trying to find the probability of.
Will that be on the test? Will this box up here be on the test?
This right here?
Yeah.
That is a good question. I don't know the answer to yet. That is a valid point for me to consider. Because I kind of, at this point, we're beginners, right?
Yeah.
And if you have this box, it's pretty easy to figure out. If the box isn't provided, it's going to require a little bit of memorization, isn't it? So, I don't know. I haven't thought that far ahead. So, we'll see. Okay, let's check B. Okay. Again, is this a binomial experiment? In a class of 23 students, 7 students completed the term project. 2 students selected at random have to give presentations. Success, notice they're telling us, is that the student has completed the project. Okay? So, I'm going to go through each of my check boxes. Okay? First of all, are there 2 outcomes? 2 outcomes?
Yeah. Yeah.
Success is
And they completed the
they
project.
completed the project. So what's the opposite of success? Okay. So 2 outcomes. They either completed or did not complete. Okay. So we can check off. That's a check in my brain. Okay. Are the results independent events? What are we picking students to do?
Present.
Present, yes.
Once you present it, so yeah, don't forget.
I mean, you can still present it.
So it's not because that would change.
Okay. So what's the probability of the first presenter? Probability of the first person presenting that has completed the project is what? 7 out of 23. What's the probability of the second person presenting?
6 out of 20.
Okay. We can argue about the top, whether it's a 6 or a 7, but the denominator is a 22, yes?
Change.
Okay, that changed. Is my probability going to be the same? No.
Nope.
Okay, and so I'm fine with putting 6 out of 22 there. We can also argue 7 out of 22 because what if the first person didn't actually present, right? But regardless, are those the same? Okay, those are not the same. So at this point, we found out that the events are not independent and not equal. So this takes out both the second and third pieces, doesn't it?
Yeah.
Which are very much related to each other. Non-independent, the probabilities are not going to be the same. So this is not a binomial experiment. Okay? Not a binomial experiment. Okay, there's two more at the top of the next page to think through real quick about whether or not they are binomial experiments. So if you look at A real quick, you select a card at random from a set of 7 cards, 4 labeled A and 3 labeled B. Then you select another card at random from the cards that remain. For each selection, success is that the card is labeled A. Is this a binomial experiment?
No.
Already you're saying no. Why not?
It's not.
Okay. You select another card from the cards that remain. What does that indicate?
That means you don't put that.
You didn't put it back. So they're not independent events. The first event is dependent on the second event, and that means that second probability is going to be different. Okay. So I agree. This is not a binomial experiment. So you're getting better at this, right? We didn't have to go through all the pieces. You could kind of scan and know exactly where we're going. Not a binomial experiment. And I'm going to say events are not independent. Okay? Okay. B, when you're ready. You roll a standard number cube 4 times. Assume that each time you roll the number cube, each number is equally likely to come up. For each roll, success is getting an even number.
Yeah.
No big red flags yet?
No.
Okay, so kind of go through your checklist, whether you write it down or whether you just think through it in your brain. Are there 2 outcomes?
Yeah.
What are my 2 outcomes?
Even not.
Even, or I'm going to say not even, but that does turn into even and odd, yes. So 2 outcomes is good. Okay, even or not even. Okay, independent.
Yeah.
1 roll of a die does not affect the next roll of the die, correct?
Correct.
So that is independent. And then what about probability of a success? Is it going to be the same every time? Probability of a success is probability of getting an even number. What is the probability of giving an even number?
3. It's a half, right?
3 out of 6, which becomes 1/2. Is it always that way? Yeah. Each time we roll the die, you have all 6 sides. You're going to have all the options there. So it is always 1/2 each time. Okay. So is this a binomial experiment? Yes, this is a binomial experiment. Okay, so when they ask you, is it a binomial experiment? Yes, it is. Okay. Got that idea going into this next section, right? Because the next section, we introduce a formula. Okay? And this is a formula to find the probability in a binomial experiment. Now, with that in mind, before you can use this formula, you have to make sure that it is a binomial experiment. If it's not a binomial experiment, we can't use the formula. But you always want to make sure it is a binomial experiment. Now, I think, do I have, yes, I have this on the next page. So, for a binomial experiment consisting of n trials with a probability of success p for each trial, the probability of exactly r successes out of the n trials is given by the following formula. Okay, so n trials is how many times it's being done. P represents the probability, and R represents the number of successes, what you're finding the probability of, essentially. Okay. When I look at the formula, okay, this is the filling in the pieces. This is kind of written out in words. When you look at this formula, there's 3 pieces. Ways to get R successes and N trials. We're going to go back and doing those combinations again, NCR. And then you have this next piece, which is P to the R. So that's your probability, so we'll use decimals or fractions, raised to R. How many times are we trying to go for success? And then the third part is the 1 minus P, which will be the opposite of probability, raised to the N minus R. Okay, so we're going to go through those 3 pieces. Best thing for me to do is go through the example here. Okay, if you can fill in the formula, all is good. Am I going to give you the formula in the test? I don't know. I would guess likely on this one. Okay, have I really thought about it yet? No, I'm not at that point. But if I had to guess on this one, I would think I might. So, okay, let's look at this. A grocery store gives away scratch-off cards with a purchase of more than $100. Terrell has 5 scratch-off cards. What is the probability that he has exactly 3 winning cards if each card has a 30% chance of being a winner? Now, do a quick check.
That's over.
Is this a binomial experiment? Okay, which I don't know if they would give you one that's not a binomial experiment and ask you to do this, but are there 2 outcomes?
Yeah.
What are my 2 outcomes?
A winning card and a
Okay, a winning card and a not winning card, right? Are the events independent? Is whether one card wins or doesn't win affect whether the next card wins or doesn't win? No, they're scratch-off cards, guys. Okay, is it probably going to be the same each time? Yeah, you're going to have equal probabilities. You always have what % chance of winning? If we look at success versus non-success, 50%, right? Either you win or you don't win. Okay, so I kind of did a quick check there. Is it a binomial experiment? It is. Okay, we were able to check off. We talked about them, right? Each of the 3 boxes, so to speak. Now, so let's decide. We need to know what N, P, and R, what each of those values are. So what did they give me here? What's the chance of being a winner?
30.
30% chance. What is that then? That is your not your R. If you have a 30% chance of being a winner, that is the likelihood that you're going to win. So that is the probability. Now, you guys realize we're not going to use 30% in the formula, though. What am I going to use to represent 30%?
0.3.
0.3. So my p-value is 0.3. N and R. Think in terms of we're going to be filling in NCR. How many times are we picking from? How many successes are we looking at? How many times are we picking from? Terrell has 5 scratch-off cards here. So N is 5. How many times are we examining this?
3.
Or looking for? Okay, success, we're looking for 3 successes. So R is 3. There's all the information you need to know right there. N is 5, R is 3, and P is 0.3. We're going to fill in the formula. So we're trying to find the probability of 3 winning cards. So NCR, 5C3, times P to the R. So that is 0.3 raised to the third, times 1 minus P. So that's going to be 1 minus 0.7 raised to the N minus R. So raised to the 5 minus 3. All I did is fill in the formula as is. I didn't do anything fancy right now. Are we okay with how I filled in the formula?
Why'd you put 0.7?
Because my brain was thinking ahead. Valid question. It should not be 0.7 here. What should it still be right here?
0.3.
0.3. Do you see where I thought ahead and goofed
Yeah.
up? Okay. So it should still at that point be 1 minus 0.3. Thank you. Okay. Now, let's do a little bit of cleanup. 5C3. How do we figure out 5C3?
Calculator.
Go for it. What's the calculator say a combination of 5 objects picked 3 at a time is?
10.
Calculator says 10, yes?
What do you give it?
Now, I'm honestly going to leave this as 0.3 raised to the third for a moment. I'll come back and put it in the calculator here in a moment. In this other parentheses, what is 1 minus 0.3? There's a 0.7, and that's going to be raised to the second. You can enter that all in your calculator in one big fell swoop right here, yes?
Yes.
You can do 10 times 0.3 to the third times 0.7 to the second. Should be able to. If you can get your calculators to cooperate. What are we getting?
0.2.
That's what I have written down.
Yeah.
Okay, so try the calculator.
Got
If you figured out how to hit the right buttons on your calculator, 0.1323. If not, maybe I need to demonstrate on the calculator, I'm not sure. What is that approximately to the nearest whole percent?
13%.
Okay, guys. There's your example of how you use that formula. Okay, definitely encourage you to try the calculator here. Now, part B. Not labeled as part B, but essentially it's part B. This next one says to the nearest tenth of a percent, what's the probability that Terrell has more than 3 winning cards? What does more than 3 mean?
3-0. Or before nothing.
Okay. So more than 3 would be 4 and 5. Okay, guys, in this situation, when it says exactly 3 winning cards, piece of cake, we're finding P of 3. In order to do probability of more than 3, you have to do a little bit of extra work. Calculator's going to be our friend, though, because we have to do probability of 4 plus probability of 5. So the formula will not allow us to do 3 or more at one time. You have to find the individual pieces. So you're going to use the formula to find probability of 4, and the formula to find probability of 5, and then you're going to have to add those. Okay? Now, good news, we already have all the information from last time, yes? And so if we go through and do probability of 4, that just means that now instead of R being 3, R is 4, yes? So P of 4, NCR, 5C4, P to the R, so that's 0.3 to the fourth. One minus P, so 1 minus 0.3 to the N minus R, so to 5 minus 4. Let's see. 5C4, have you done the math? Should be 5. I'm going to leave it as 0.3 to the fourth for right now. And then 1 minus 0.3 is going to be 0.7 to the first. Put it in on your calculator, yes? Calculator says 0. I have 0.02835. Okay. And then can you repeat the process for a probability of 5? Okay, so now we're talking about probability that all of his cards are winners. So probability of 5, now my R value is 5. So we're doing 5C5. Times 0.3 to the fifth times 1 minus 0.3 to the 5 minus 5. (5C5), we do that in the calculator. Order doesn't matter. The options of picking 5 objects, 5 at a time, there is just 1. 0.3 to the 5 is still going to be in the middle there. And then this is going to be 0.7 to the 0. What is anything raised to 0? 1. So what's the only piece you really need to do here? 0.3 to the 5 is all you really need to do. And what is 0.3 to the 5? 0 point something. I have 0.00243. So what are we going to do to find the probability of more than 3? We're going to take these two probabilities, 0.02835, and we're going to add it to 0.00243. Notice I didn't add too soon. If I add those too soon, you could run into trouble. Okay, so I didn't round them too soon, I meant. 0.03078, which is approximately what? Now this one says in here it's 0.1%.
30.8%.
Well, 7 tells the 0 to go up, so 3.1%. Okay. Okay, guys. I've kind of run out of time for the last one, but the last one is just a repeat example of how to do this, okay? And I'll go ahead and fill this in a little bit, but I will tell you your homework is available in Savas. Lesson 12.4 in Savas. Get it done for tomorrow, please. If you look at this last one, your N is 6. Probability she gets a vowel exactly 3 times. R is 3. And you actually have to find the probability on this one. It wasn't provided. So probability of a vowel. Looks like probability of a vowel is 2 out of 7. So when you use your probability here, that is going to be 2/7. Okay, so keep in mind you might have to actually find your own probability. So I'm going to go ahead and set this up. So it'll be on the video if you want to go back and look at it. So probability of 3, 6C3, P to the R. So 2/7 to the 3, and then 1 minus P, 1 minus 2/7 to the N minus R, so 6 minus 3. 20 times 2/7 to the third times 5/7 to the third.
What? No.
0.169979195 for an approximate answer. Whoops.
They must start. Have a good day.
Of 17%.